On? Recorded? Okay, good. So today we're going to go through that part where how a single slit effect affects the double slit pattern. We have gone through it, but I thought I will just go through it again because it's an important idea. Okay, still remember the first single slit pattern, it looks like this. This is intensity, this is the angle. Yeah, we've gone through this before. You should be familiar with this. We derived this via the IB method and also via the complex number method. Okay, rather complex. So the idea over here is that if I got a two slit pattern, the ideal case, remember that it is like this. That's the ideal case, where the fringes are evenly bright and they're evenly spaced. But I'm going to show to you in a short while that it is not the case. Yeah, it actually looks something quite different. And I'll explain to you why. So let's take a look. First of all, you must realize that the two slits over here, they are probably about 10 to the power minus 4 millimeters apart. So what am I trying to say? Basically, they are almost together. I'm exaggerating the separation between them so that we can see two slits. If I were to draw them at 10 to the power minus 4 mm apart, you can't see the slits. Yeah, so you must remember that they're almost together. So which means that the light from each of them will overlap. That's what I'm trying to say. Okay, they overlap each other. So say for example, the intensity of light from slit A looks like this. Then the intensity of light from slit B will look identical. Assuming of course the slit width and everything else being the same. Cool? So what we have over here is that consider 2 points X and Y. Do you agree that the intensity, if this is a constructive interference, it will be, and this is also constructive interference, assuming that it is, do you agree that the resultant intensity of the constructive interference here will be higher than the constructive interference, the resulting intensity over here? Both are constructive interference, but because the intensity of the light arriving here is higher, the constructive interference intensity will be higher than the constructive interference over here. And over here, say for example, Z is another point where it's constructive interference, which means that the I resultant at X is going to be bigger than the I resultant at Y, which is bigger than I resultant at Z, if all of them are constructive interference, which is quite different from what we talk about over here. Over here, we talk about that the intensity is always constant. So therefore, how will the intensity pattern look like? The resultant intensity pattern looks like this. You've got the envelope over here, and the intensity looks like this. So the word to use is that the intensity of the double slit, this is the phrasing that we usually use, intensity of the two slit pattern. Still remember what's the word? It starts with M. Modulated, yes, correct. Is modulated by the single slit pattern. So this is the phrase to describe this. You need to understand when IB says that the intensity is modulated by this, it means that they're talking about this. A test of whether you, okay, probably before we go to test, let us be clear about certain things about this pattern first. Okay? You must realize that there are two minimums that you need to be careful of. The first over here, and the other one, okay, probably this one and this one. There are two distances over here. This we call it delta x1, this we call it delta x2. Okay, there are two distances you need to be very careful about. Delta x1 is due to single slit or double slit? Double slit, exactly. So if you remember the formula for delta x1 is equals to L lambda upon D. This being the wavelength, this being the slit width or separation. Separation, correct. You need to be very, whenever you look at the equation, right, it is very important that you tag it, you must say it out. You must literally say it out in clear words and form that this is slit separation. You need to tag it verbally, the audio file needs to be there, the visual file needs to be there. Yeah, so that you are clear. It's slit separation. Now, you got a problem over there? You okay? Okay, huh? Okay, good. Now, delta x2 over here is actually equals to, remember the angle to the first minima is lambda upon D. Now this is slit width, yes, correct. And then you multiply by L as well. Why? Because if this is the angle to the first minima, if this is theta, which is d equals to lambda upon d, where this is slit width, how do I find this one, which is delta x2? I multiply this angle by the screen separation, which is L. So actually it's L times theta, and theta is lambda upon slit width. Clear? Because they are both d. Must be very crystal clear about this one. This is slit width. Therefore, from this diagram, 1 delta x1, 2 delta x1, 3 delta x1, about 4 delta x1, about 4 of them. Yeah, it's not very clear which one it coincides. Probably 4 or 3.5. Let's assume it's 4. So for this one, it's 4 delta x1 equals to delta x2. What can we deduce out of it? The, let's say, separation is equals to L lambda d width. So I cancel. I will know that d width is actually equals to d separation divided by 4. So just by looking at the pattern, I can deduce this. Cool? Yeah. And you need to know how to deduce these kind of things. First, you need to know which pattern is due to which. This is due to the double slit, and this big envelope is due to the single slit. First point. Second point, from the information given in the graph, I need to be able to deduce the approximate relative size of the slit width and the slit separation. Cool. Now, is it fair of you to deduce, because it's not very clear over here? I think to be fair, the question should tell you that this is the position of the fourth maxima, if it is an ideal situation. I think the question should tell you. Or otherwise, it should be very clear to you where the maxima is. Whether this is the fourth maxima or fifth maxima or sixth maxima. Okay? Okay, up to now, Ken? So whatever I'm doing over here is to explain to you the actual two-slit pattern you'll be observing, which is this one, not this one. So question over here, how do you get from here to here? What should you do? You eliminate, can you eliminate the single slit pattern? How do you get this to approximate to this? You make something really small. Yes, you make the slit width really small. Why? Why is it that, yeah? Yes, please go ahead. Between the center of A to the center of B, center to center. The size, yes, correct. The size of the width, slit width, yes, correct. Must be very clear about that, yeah? I love to set questions on this. Yeah, because that's where things get confused. And that's where students who actually memorize equations without knowing what the terms mean will get tricked. Okay? So don't be one of those who fall into that trick. So we haven't answered the question, how do you get this to approximate to this? You make the slit width really, really small. But what's the catch? If you make the slit width really, really small, the intensity gets low. Yes, correct. So the perfect pattern is the pattern you never get to see. Like what I said last time. Okay? Cool? It's just hypothetical. Just like ideal guess. There's no such thing called ideal guess. Yeah, it's ideal. Just like the ideal partner. Okay, this is a little bit far, but okay, Ken, this section finished. Before we move on, any other questions? Cool? Okay, good. There'll be time later on for you to ask questions on a personal level. So if you have any questions that you have but you don't dare to ask right now, you can always ask me later on. Now the next part I'm going to go to is how the two slits will behave if we go from 1 to 2 and then 2 to 3. Okay, let's take a look, yeah? So if I got a two-slit pattern over here, I'm going to have, let's consider the ideal case, you're going to have this. Yeah? Let's consider ideal case. The non-ideal case is a little bit complicated, so let's consider ideal case for simplicity, so that we understand the concept rather than the math of it. So if it is an ideal two-slit pattern, it looks like this. Now, let's take a look at this position. The interesting part is this position. Now, this position is constructive or destructive? Yes, destructive. Now, which means that the light from A and B interfere destructively over here. Now, what happens if I were to put a third slit at the same separation away? That means this is D, and this is your slit C. This is slit B, this is slit A. Do you agree that at the same positions where the maximus are, the maximus will still be maximus? Do you agree that the maximus will still be maximus? Why? Because the reason why these are maximus is because the path difference from here to here is one wavelength. The path difference over here will be two wavelengths, not half. Why? First of all, it is a maxima. If it is maxima, it should satisfy m lambda. Yeah, and it is the second one after the center one, so it's 2 lambda. Okay? Now, do you agree that at this position, the path difference between A and B is 1 lambda? And the path difference between B and C is also 1 lambda, because it's the same separation. And therefore, A and C will be 2 lambda. So all of them satisfy the constructive interference condition. So whatever that is maxima over here will be maxima over here. Now let's take a look at what's interesting, which is somewhere in between. Somewhere in between, previously, A and B cancels off each other. But now you got a C, a third party. All right, you got a third party. So the intensity over here is not 0. A and B cancels out, but you still got C. So that's why the pattern will look like this. In between the maximas, you've got a secondary maxima. But how do we prove this more rigorously? I don't think we should be satisfied with the idea that because A and B cancels out, so C actually there is another one there. And that's when I went on to use the phasor diagram. You remember that? Yeah. Remember? Okay, let me just... Do you want to try and do it yourself? I don't want to destroy my morning. It's a beautiful morning, don't destroy it. Okay, let me try it. So this is theta, this is d. Do you agree? The same method that this is the path difference, which is equals to d sine theta. So they meet at the point over here. So corresponding phase difference is equals to 2 pi upon lambda d sine theta. So this is the phase difference between the light coming from A and B. Now, the phasor method is basically to represent the intensity of the light, or to represent the relationship between the different light sources using a vector diagram. Yeah? So let's take this to be the light coming from A, and then this to be the light coming from B, and it is at a phase angle of phi. That's the method. And therefore C, you will have A of C, which is also at phi away, and therefore the resultant intensity is here. The resultant amplitude is there. You okay? Now it can be proven that this is also phi, this is also phi. Therefore, if you want to find the resultant amplitude, it is equals to A cos phi times 2 plus 1 plus A. Yep. Why? Because this is A. This is A cos phi, A cos phi. Still cool? Okay. Therefore, you can actually bring A out is 2 cos phi plus 1. How does a phi cos graph, how does a cos graph look like? Let's call it Y. So it's going to go like this, yeah? So this is going to be, if it is 2 cos phi, it will be 2 minus 2. Now, if I were to take this plus 1, it's going to look like this. 3 and minus 1. Make sense? Now, if I were to square this, because intensity is proportional to AR square. So if I square this graph, how is it going to look like? It's going to look like, which is exactly what we have over there. Does it make sense? Hang on, does it make sense? This is going to be 9, this is going to be 1. That means the intensity ratio between this and this is 9 is to 1. Check. This is the position where all the 3A's add up constructively. So the resultant amplitude is 3A. This is the part where A and B interfere destructively, but you got C coming in there. So it's A versus 3A. If you square it, the ratio is 9. Amplitude intensity is proportional to amplitude square. This is 3A, this is A. Sorry?
There's a constant somewhere. That's ratio, not
The ratio, that's why I said ratio. It's not absolute value. It's not 9 watts per meter square. If you take the ratio of the intensity, it's 9:1. You can do this for the 4 slits, 5 slits, 6 slits, but you just get a little bit more complicated. Yeah, actually not a little bit more. It's actually much more complicated. Yeah. Which one? Oh, because remember this is the amplitude. How do I get this? You mean? This one basically this is A, which is the amplitude over here. This is A cos phi, you get this one, times 2. So this is A cos phi, A cos phi. So it's 2A cos phi plus A. Oh, because remember the phasor diagram, the phasor method is you represent the amplitude of light sources from each of the slit by vectors. And how do you represent the phase angle between the two of them? You basically shift one of them by phi. Then you shift the next one by phi. Because A and B, the phase is phi. B and C, the phase is phi. Yeah. Okay? So that's the method. Yeah, that's the method. It's a, I think, rather simple method. Once you grasp the idea behind it, it's actually not a very difficult method. But as you can see, once I have a 4-slit system, it's going to get progressively even more complicated. Yeah? Ken? Cool. Then basically what I went on from there is to show you that when you have infinite number of slits, you get this pattern. You get the diffraction pattern, diffraction grading pattern, which is sharply defined and very bright. Yeah, if you remember that part. Sorry, phasor diagram. Which one again? For which one? Oh, for n number of slits, it's going to be very complicated. If it is n number of slits, I recommend the complex number method. Because phase diagram, can you see that it's going to be whoa, it's going to, yeah. It's just not practical anymore. Sorry? If there is a lot of slits. Yeah, that's why I recommend not to use the phasor diagram if it is too many slits. Yep. It will not come back to this point. Yeah, it will not come back to this point, depending on what's your phi.
So when your n increases to very large waveforms,
no, it doesn't close up. If you try, it shouldn't close up. Yeah. No, it may not even be a semicircle because if you keep on adding phi, it depends on what's the phi. Because at different positions on the screen, you have different phi values. So at some position, it may be 0. At some position, it may not be 0. Yes, you see, the thing is that n is equals to infinity, that's one thing. But the other thing you need to consider is that it also depends on the phi over here. If the phi is 2 pi or 0, then it will actually just add up in a straight line. So it depends on your phi. It will determine how you add up. Okay? Any remaining questions? Otherwise, I think you can stop recording now. Thank you.